So, good morning, everyone. Today, we are going to see the fascinating world of heat transfer, a fundamental concept in engineering and physics. Heat transfer is all about how thermal energy moves from one object to another, driven by temperature differences. This process is critical in everything from designing efficient cooling systems to understanding natural phenomena like weather patterns. We will explore the three primary modes of heat transfer: conduction, convection, and radiation. Each mode operates differently, and understanding them is a key to solve real-world problems, such as improving energy efficiency or developing advanced materials. By the end of this lecture, you will have a solid grasp of how these mechanisms work and where they apply in everyday life. Let's start by setting the governing equations which determines or tells us how the heat energy flows, whether that is a solid, a fluid, or even an empty space. We will break down each mode with clear definitions, mathematical laws, and practical examples to make the concept retailable. Whether we are an aspiring engineer or just curious about how heat works, this lecture will provide a strong foundation. Get ready to see how heat transfer shapes the real world around us, from the warmth of your coffee cups to the cooling of the massive industrial systems. So let's move to see the next slide to give a deeper insights on what heat transfer is and why it matters. Now, as we are going to see these basic modes, before that, we will see what is meant by heat transfer. So let's begin with the basics of heat transfer. Heat transfer is the movement of thermal energy between objects or systems due to a temperature difference. Think of a hot pan on a stove. The heat moves from the burner to the pan because the burner is hotter. And this process is universal, occurring in nature and technology alike. There are three main ways heat is transferred. The first is conduction, second is convection, and third is radiation. The conduction happens when heat travels through a solid material, like a metal spoon heating up in a hot pot. Convection involves heat moving through fluids, like liquids or gases, often due to the motion of fluid itself, like warm air rising in a room. Radiation, on the other hand, is heat transfer through electromagnetic waves, like the warmth you feel from the sun. Each mode has unique characteristics and applications, which we will explore in detail. For now, we have to understand the heat, the mechanism of heat flow. As we have seen, heat flows from a hotter object to cooler one until the equilibrium is reached. This principle drives everything from designing car engines to creating energy efficient buildings. In engineering, mastering heat transfer allows us to optimize systems, reduce energy waste, and improve safety. Over the next few slides, we will break down each mode of heat transfer, starting with conduction, and discuss the laws which govern them. By understanding this mechanism, you will see how they work in real-world scenarios, from cooking to climate control. Now let's start with conduction, the first mode of heat transfer. Conduction occurs when heat moves through a material without the moving of material itself. And it's the most common in solids where molecules vibrate and pass energy to their neighbors. Imagine touching a hot metal rod. The heat travels from the hot end to your hand through molecular collisions. This process is governed by Fourier's law, which states that the heat flux Q is proportional to the temperature gradient dt by dx and the material's thermal conductivity K. The negative sign indicates heat flows from hot to cold. Materials like metals with high thermal conductivity are excellent conductors, while insulators like wood or foam resist heat flow. Conduction is critical in applications like designing heat sinks for electronics or insulating buildings to save energy. For example, a copper pipe conducts heat faster than a plastic one, making it ideal for heat exchangers. Understanding conductions helps engineers to select materials for specific purposes, balancing efficiency and cost. In daily life, you experience conduction when you feel the warmth of a heated seat or the chill of an ice cube. Over the next slide, we will look at real-world examples to solidify this concept and see how conduction shapes our environment. Now let's begin conduction to our daily life with some practical examples. First, consider heating one end of a metal rod. If you hold a steel rod over a flame, the heat travels along the rod, making the other end hot. This is conduction at work. As the metal molecules transfer energy, another example is cooking on a stove. When you place a pan on a hot burner, heat conducts from the burner to the pan, warming the food inside. The pan material like aluminum is chosen for its high thermal conductivity. Finally, think about the heat transfer through building walls. In winter, heat from your home conducts through the walls to the cold outside, which is why insulation is crucial. Materials like fiberglass slow conduction, keeping your home warm and reducing energy bills. These examples show how conduction affects both everyday life and engineering design, whether it's choosing cookware or designing energy-efficient homes. Understanding conduction helps make informed decisions. Next, we will see or explore the convection, another mode of heat transfer that involves the fluid motion. Moving on to convection. This mode of heat transfer involves the movement of fluids, liquids, or gases. Unlike conduction, where the material stays still, convection relies on the fluid motion to carry heat. There are two types. One is the natural and other is the forced convection. Natural convection helps when fluid density changes with temperature, causing warmer, less dense fluid to rise and cool. Denser fluid goes at the bottom or sinks, and this causes a gradient difference, and which is due to which this gradient difference initiate the motion of the fluid, and this motion of the fluid causes the heat transfer from one location to another location. Now think of a pot of boiling water. The water rises, creating currents. Now, in case of forced convection, on the other hand, we use external devices like fans or pumps to move the fluid, as in the car's radiator. The convection is governed by the Newton's law of cooling, where or which relates heat transfer rate Q to the surface area of the body, the temperature difference between the surface of the body and the surrounding fluid. It is given by Ts minus Tf, where Ts is the surface temperature of the body and Tf is the temperature of the fluid which is surrounding the body, and the convection heat transfer coefficient H. This law helps the engineers to design systems like air conditioners or heat exchangers. Convection is everywhere, from ocean currents to the cooling of your laptop. Understanding convection allows us to optimize the systems for efficiency and performance. Now, let's look some example on the next slide to see convection in action. Let's explore the convection through real-world examples. First, consider the boiling water in a pot. As the water heats, warmer water rises to the surface while the cooler water sinks, creating a circular flow that distributes heat. This is a natural convection driven by density difference. Another example is wind currents affecting body temperature. On a chill day, moving air by forced convection carries heat from your skin, making you feel cooler. Finally, think about a car's cooling systems. The radiator uses forced convection with a fan pushing air through the radiator fins to remove the heat from the engine coolant. This ensures the engine doesn't overheat. These examples highlight the convection role in both nature and technology. From cooking to climate control, the convection shapes how heat moves in fluids. Next, we will see the radiation, which is the important mode of heat transfer, which doesn't require a medium at all. Now let's discuss radiation, the third mode of heat transfer. Unlike conduction and convection, radiation doesn't need a medium. It transfers heat through electromagnetic waves, primarily in the infrared spectrum. This is how the sun's heat reaches Earth across the vacuum of space. Radiation is governed by Stefan Boltzmann law, which states that the heat emitted Q is proportional to the surface area A and the fourth power of the absolute temperature, that is T raised to 4, multiplied by the emissivity epsilon and the Stefan Boltzmann constant sigma. Emissivity depends on the material surface properties. Shiny surface emits less, while a dark one emits more. Radiation is unique because it can occur in a vacuum and insignificant at high temperatures. It's critical in applications like solar panels, where capturing radiant energy from the sun, is very much crucial. Or in designing the spacecrafts, where heat must be radiated away in the space. Radiation affects daily life too, from the warmth of a fire to the glow of a light bulb. Let's look at some example to see how radiation works in practice. Let's illustrate radiation with some familiar example. First, the heat from the sun reaching Earth is a classic case. Solar energy travels millions of miles through the space as electromagnetic waves warming our planet. Another example is infrared heaters, which emit radiant heat to warm objects and people directly without heating the air. Finally, consider the heat emitted by a fire or a light bulb. When you sit by a campfire, you feel warmth from the infrared radiation it emits, even if the surrounding air is cool. Similarly, an incandescent bulb radiates heat alongside light. These examples show radiation's ability to transfer heat over the distances and through a vacuum. In engineering, understanding radiation helps to design systems like thermal shields or energy-efficient windows that reflect infrared waves. Next, we will explore how all the three modes such as conduction, convection, and radiations combine in the real-world scenarios. In the real world, heat transfer rarely happens through just one mode, which is conduction, convection, and radiation. And often these different modes often work together. Let's take hot cup of coffee as an example. First, conduction transfer heat from the hot coffee to the cooler cup through direct contact. The cup material like ceramic conducts heat to the outer surface. Second, the convection occurs as hot coffee warms the air above it, causing natural convection currents, which cools the coffee down over the time. In engineering, understanding this interaction is crucial for designing systems like heat exchanger, where all the three modes are accounted to maximize the efficiency. Now, in this case, we have not discussed the radiations. We have discussed the conduction mode of heat transfer, okay, which causes the hot cup to get warm by the hot coffee by the conduction mode of heat transfer. Now, if you blow air on the coffee by your mouth, which is considered as the forced convection, which speeds up the heat loss. And finally, the radiation plays a role as the hot coffee and the cup emit the infrared waves to the surrounding. Now see, these are the combined effects which causes the hot coffee to get cooled by using the three modes of heat transfer, conduction, convection, and radiation, which all are working together in the action. And this combined effect is why the coffee cools down over the time. In engineering, understanding this interaction is crucial for designing the systems like the heat exchangers, where all the three modes must be accounted to maximize the efficiency. Whether it's a car engine, a refrigerator, or buildings HVAC systems, multiple heat transfer modes are always there. This complexity makes heat transfer both challenging and exciting to study. Now let's wrap up why this matters in engineering and in our daily life. Now, as we all know, heat transfer is an important concept of engineering and everyday life. By understanding conduction, convection, and radiation, we can design systems that manage thermal energy effectively. Conduction helps us to choose material for heat sinks or insulation. Convection is key in cooling systems, from radiators to the air conditioners. Radiation informs design for solar panels or thermal protections in the spacecrafts. These principles have wide range applications. HVAC systems keeps the buildings comfortable, insulation reduces the energy cost, and the heat transfer knowledge enhances the cooking technique. In industries like aerospace, automotive, electronics, optimizing heat transfer improves the performance and safety. Even in nature, heat transfer drives weather patterns and ocean currents. As engineer, mastering these concepts allows us to innovate and solve pressing challenges like developing sustainable energy solutions. I hope this lecture has sparked your curiosity about heat transfer and its impact. For the next class, think about how these modes apply to a system you encounter daily, like your car or your kitchen. Thank you, and let's continue exploring the science of heat.